Hello everyone. Today I'll be explaining how my project Medusa anti-cheat works, and specifically I'll be going over the reach detection aspect of Medusa anti-cheat and more about the system design. In the end, I'll show a live demo of the detection in action, so if you want to see that, skip to the end. So first we have to go over what are reach cheats. Reach cheats are an unfair advantage gained in online gaming through illegally modified clients. Reach cheats involve extra attack distance during combat, and if you don't know anything about cheating in online games or anti-cheats or the industry in general, I like to imagine it as a boxing match. So you can see here that the red guy has a much longer arm and the blue guy has a much shorter arm. And because of that, if this were to be like a real life boxing match, the red guy would just have the advantage the whole time if we ignored, every other factor out there. He just has more reach, the blue guy cannot reach him. You will never be able to come within distance where he can actually attack the red guy, and the red guy is just going to win the fight every single time. Well, in an online gaming environment, every single player is supposed to be on the same playing field. That's why in games like Minecraft, which is the game that Medusa anti-cheat runs on, the default reach is 3 meters. And if you were to use some sort of cheat that modified your reach to become 4 meters, you would gain a very significant advantage. And now you're probably thinking like, okay, but who really cares about this? Well, cheaters ruin the gameplay experience for others, not just in online gaming, but also in real life sports. So, for example, if someone is, a boxer or a sprinter, Olympic runner, or whatever, and they're using a performance enhancing drug, some kind of stimulant to give them more stamina or whatever, then that's an unfair advantage because they're gaining an advantage where other people did not have access to this performance enhancing drug. And it's the same concept for, for servers, right? So there are players that don't have access to the reach cheats that this cheater is using, and that's an unfair advantage. And if you are confused what an entity exactly is, I like to use an entity versus antivirus analogy. Everybody has a computer, and everyone knows if you get a virus on a computer, that is the last thing that you want to deal with. Virus on your computer means your computer is going to slow down, your computer is going to have a bunch of pop-ups, your files may get deleted, and overall, you're just not going to enjoy the experience of using your computer. The same way, if there is a cheater on your, online competitive gaming server, then that ruins the gameplay experience for others. People are not going to be able to compete with the cheater, and they're just not going to enjoy the experience of playing on your server. And then you're going to lose profits because players are going to leave your server for other servers that have better anti-cheats, and it just sucks for everyone. So now I'll go over the basic detection and mitigation idea. This is the most bare bones basic detection that it gets for a reach check. And the idea is basically that we will check the distance between the player eye and the target hitbox, and we'll see if it exceeds the default value, which is 3 meters, and if it is, we'll immediately remove them from the game. And that all sounds great in theory, but there's some complications to it, just like any problem in the real world. And the two biggest complications are latency and the false positive potential, or the FPP. So I'll go over some solutions to fix both those problems. First, I'll discuss how to fix the problem of latency, and this is a concept called rewind time latency compensation, right? So the problem of latency is that the server will send the target positions to the client. However, there's some latency between the client and the server that causes them to be out of sync. Therefore, what the server thinks the client is seeing is completely out of sync with what the client is actually seeing. And therefore, we need some kind of system that can mitigate the effect of latency for our reach detection. So what we'll do is we will store a sliding window of n target positions over time. This can be any amount of target positions. So depending on how much lag that you want to account for, you may want to account for 10 seconds of lag, 20 seconds of lag, 30 seconds of lag. In this particular example, to keep it a bit simpler, we're only going to account for about a half second of lag. The more lag you want to account for, the bigger the sliding window is going to be, the more memory it's going to take, and the more resources, it's going to be harder to scale up for more players and more positions that you're going to store in this window. So On top of that, every 50 milliseconds, the server sends a new position, and this is not by design of the anti-cheat. This is just something that is imposed on the server software that already was existing. And the idea of this uh, concept is that we will rewind to the most likely subset of boxes, or most likely subset of target positions based on the player latency. So to give an example here, let's say that you, the player, has an average latency of 163 milliseconds, and give or take 40 milliseconds. So that means that we have a what I like to call compensation range of 123 milliseconds to 203 milliseconds. Now, before we move on, I want you to take note that the server is only sending positions every 50 milliseconds. So if we were to use this range to select boxes right now without any kind of rounding or quantization, we wouldn't actually know what the proper subset of boxes is. Because, for example, let's take this lower bound of 123 milliseconds. If we take that bound, we will be almost exactly in between the 150 millisecond box and the 100 millisecond box. And then at that point, you have to decide, okay, do I include, in my subset, the 100 millisecond box or not? And to reduce false positives, what we'll do to reduce false positives is we will assume the worst case, which is, yes, we will include this box in our subset at the expense of a little bit of detection accuracy, but we will gain a massive benefit in reducing false positives. It's the same thing at the upper bound here. So 203 milliseconds, I'm just in between the 200 millisecond position and the 250 millisecond position. And again, to reduce the likelihood of false positives greatly for a little bit of detection trade-off, we will assume the worst case and include the 250 millisecond box as well. And so we end up with a rounding. After rounding, we end up with 100 millisecond as the lower bound and 250 millisecond as the upper bound. And then you can see we have visualization of the selected compensation range. So these four boxes, the 100, 150, 200, 250 box, are the four boxes which we will select and do our calculations on. And the basic idea is after you have selected this subset of boxes, you will check the minimum distance to each box, right? So we will create a minimum distance, and then for every box in the subset, we will calculate the distance, and if that distance is less than the minimum distance, we will update the minimum distance. And that will lead us to have, for all of these boxes, the minimum distance. And then if the minimum distance is more than 3 blocks, we will alert. And that seems like a pretty good idea in theory, but again, there's a little bit more to it than just that. This is actually going to cause a ton of false positives because we don't have a perfect view of what the client is actually doing, or rather the client's the properties of the client. So we may be able to collect, information such as the average latency or the uncertainty of the latency, and we may be able to collect information such as the, n most recent target positions for the client. But the discrepancy here is pretty massive still between the server and the client. For example, we won't always have, a true representation of the actual server to client or client to server latency. Whether that's in the mean or the uncertainty, both of these values can be inaccurate to a degree. But the really big part here is that the server only sends positions to the client every 50 milliseconds. But the client actually performs some sort of interpolation between these positions to essentially smooth out the display of the target on screen, because if the server only sends every 50 milliseconds, then on the player's screen, without interpolation, they will have a very choppy visual of the target moving on their screen. And so the client applies its own kind of visualization or interpolation within the rendering that we don't have access to on the server. So that's really the big discrepancy there. We do not have a perfect view of the target position on the client screen. And because of that, we do not have a perfect algorithm, so we need to use some kind of smoothing to smooth out the distance signal and therefore reduce false positives. And the most easy to implement and easiest to understand approach is called the leaky bucket algorithm. So there's three parts to the leaky bucket algorithm: the accumulation, the leakage, and the overflow. So if you look at this code here, this is our threshold. Min distance is greater than 3 blocks, and if it is, we will accumulate an amount of, you know, unitless amount of 1 into the bucket. And then if that accumulation overflows, so our overflow threshold is 3, then we will send an alert. And then this is optional. You can reset the accumulation or empty the bucket if you want. But at the same time, while we are accumulating, we also have leakage. So the idea here is that to reduce false positives, we will make the bucket leak slightly, right? And the idea here is that if we can accumulate violations faster than the bucket can leak all of the accumulation out, then the bucket will overflow, and that will become our trigger to actually send an alert to, staff of the server, or send an alert to be stored in some kind of system that when we exceed n amount of alerts, we will ban or kick the player. So that is pretty much the entire reach detection system design. Now I'll show you what it's actually like on a server. So I'll open Minecraft here. Okay. Yep, there we go. Okay. So I will show you what the hack client looks like. This is called the vape hack client. I don't know why that's the name of the hack client, but it just is. And as you can see here, we have a module which is called reach. And like I said, the default value of reach in this game is 3 blocks. And I said also you will gain a significant advantage at 4 blocks. So I set it to 4 blocks. I'm just going to turn on my auto clicker so I don't have to waste energy clicking. And I'll show you what 4 blocks of reach looks like. And as you can see, it looks like we're hitting from pretty far away. And we're also spamming alerts in the chat. And usually what would it be on the server is if we have exceeded n amount of alerts, then I will be banned or kicked, or my packets will be rejected, basically. So right now I'm already at 50 violations. So usually by like the 20th violation or whatever you set it to, you'll be banned or kicked. So I'll log out to reset the violation level, and I'll show you what it looks like with a normal amount of reach. And by the way, you can see the actual reach value here. So this is what the client actually sees. And as you can see, we're not exceeding 3 blocks at all. And I'll just keep going here for a little bit to, ensure, show you that the check is robust. And yeah, we're not gonna false flag at all because, like I said, the check is totally robust against any latency. And on top of that, we also have another filter to smooth out the distance signal and reduce false positives. So in a real world setting, let's say maybe you were lagging and you had, I don't know, like 1000 ms, so 1 second of latency, and you had a high uncertainty, let's say of 500 milliseconds, you will only flag, and this is in something that I've actually tested, you will only flag twice, false flag twice for every 5,000 hits, which is a extremely low false positive rate and far exceeds the standard of what a typical server would want. And I'll also lower the reach setting now to, I'll turn on the reach. I'll lower the reach setting now to something that's a little bit less blatant, a little bit less obvious. And what you'll notice is that we do get a slower detection rate. However, in the end, we're still going to be detected yet. So a couple flags there. And in a few seconds, we would be banned if I had that turned on. And yeah, so at the time of violation, you'd normally be banned. I just turned it off for purpose of the demo. But yeah, it's a pretty fast detection. And we can even push in lower latency scenarios, such as right now, I'm only having about maybe 100 ms to the server. we can lower the reach violation even more. So now instead of violating by a full block or half a block like we were earlier, we are only exceeding the threshold by a quarter of a block. And I'll show you what that looks like. And we've already gotten a few flags. And you can see we're barely, if you look at the display, we're only coming just barely above 3 blocks. And to a lot of anti-cheats, this would be, virtually undetectable. And I'm also flagging autoclicker because I, have my autoclicker on. Yeah, even in a low threshold, we're still flagging. So that's pretty much it for the demo. I hope you enjoyed watching, and that's pretty much it.